Okay, so we talked about the two forms of stationary phases inside of a capillary column. All right, so that's the thing that you've got to remember. We're talking about capillary columns here, not packed columns. Packed columns are packed with chrome absorb. They are packed with different material. But capillary columns has this thin layer around the inside of the column itself, around the whole interior wall of stationary phase. And here is the stationary phase in red. And we said there's two different forms. One of these are called polysiloxanes, and then the other form is called a PEG, polyethylene glycols. So these are the two kind of basic foundational stationary phases that we can use in a capillary column. And then what happens is that once these go on, we can then modify these stationary phases, and we can put things onto the stationary phase that will help us separate things a little bit better. And we said that there was a variety pack of these things. There were tons of different choices that go onto these polysiloxanes or PEGs that allow us to separate things based on functional group or based on boiling point or based on polarity or based on structure. Whatever the case is, that will help us do our job a little bit better. Okay? So we said that there were plenty of choices, and here are some of those choices that we might see. So this is just straight 100% dimethyl polysiloxane. That's all that it is. So it is a traditional run-of-the-mill stationary phase, nothing really special on it at all. And here we got a form where they take 5% and they add a phenyl group onto it. All right, so if I go back to this picture of these polysiloxanes, here is dimethyl polysiloxane right there. So there's one methyl group, which is a CH3 on top, and one methyl group, which is a CH3 on the bottom. Well, I can modify that. Maybe this is not good enough for me. So I can go through and modify this, and I can take this 100% dimethyl polysiloxane and I can mix it with something else. So I can incorporate diphenyl into this structure. So 5% of the time, I would run across a polysiloxane that has this big ring up here at the very top and a really big ring down here at the very bottom. And then 95% of the time, I would see my traditional dimethyl polysiloxane. Okay, so that's what those numbers represent. Here, my third choice, 14% cyanopropylphenol and 86% methyl polysiloxane. Well, if I go back to this slide and take a look, there is my cyanopropylphenol structure. It's right here, okay? So here I see my siloxane backbone, and propyl means three. So one carbon, two carbon, three carbon, and a cyano is a C triple bond N functional group in chemistry. So here is my cyanopropyl on top, and then my phenyl is the same as my phenyl here. It's a ring. So on this side, it's a ring. So sometimes I can get stationary phases that's made up of 14% of that cyanopropylphenol and then 86% of my methyl polysiloxane. So these are just a couple of different choices that I could go through and maybe order as far as a capillary column goes. Over here to the side, you see why the choices exist. And this gives me relative polarity. So dimethyl polysiloxane 100%, that is basically nonpolar, right? I'm not going to really play off of functional groups. I'm not going to play off of the polarity of the compounds that I inject into the machine, which means charges. How lopsided is it? What I play off of are the strict boiling points. That's about it, right? The ones with lower boiling points turn into a gas first, and those come through the machine first. It's as simple as that. So very often in a laboratory, we either have this 100% or this 5% phenol blend, when it comes to the stationary phase of my column. These things allow me to separate things based on boiling point and just strictly boiling point. The ones with lower boiling points come off first, the ones with higher boiling points come off last. The other ones, as I increase the polarity of the column, the other ones play off of the actual functional group itself. So if it's a polar column, it's going to hold back polar molecules. And when that happens, things do not separate based on boiling point. All right, so here's the take-home message for you to remember and to jot down. First, traditionally, lower boiling points of molecules come off first. That means if I've got two molecules here, A and B, and one of my molecules has a 50-degree boiling point and the other one has a 100-degree boiling point. On my chromatogram with a traditional column, I will see two peaks. There's my first one, there's my second one. My first peak is probably the one that has the lowest boiling point, and in this case, that's A. And my later eluting peaks, those are the ones that have the highest boiling points. So that's a very kind of easy way to separate things based on boiling points. The problem, though, is that what if I have a scenario here where A and B have really close boiling points? Let's say this one's 52 degrees and this one's 57 degrees. Well, sometimes it might be difficult to separate these two because their boiling points are so close together. And a traditional column would not work for me for that reason. A traditional column might run this sample, and what you might see is something that maybe looks like this. And that's not what we want to see on a chromatogram. That's not what we've been drawing. We want single peaks that are very dominant, that's very slim and slender. Well, I've got to make this better. I've got to separate those things a little bit more. And what I can do is I can change my column stationary phase. I can begin to use some of these other stationary phases that are out here and maybe not play off of boiling point, but play off of polarity of the molecules instead. And polarity just basically means charge, right? If I get a molecule and I get a positive end on one side and a negative end on the other, we call that polar. So some molecules are more polar than others, depending on what we have, and we can treat that like boiling point. And we can change a column up, and when we change the column up, well, what can happen is that maybe, just maybe, I can improve my chromatogram, and I don't need to see this mess. Maybe by changing the column up, I can then get a clear separation of the two components. And that's why there's so many choices out there, because there's so many things that we have to analyze, and there's so many things that we can do, and we need those choices that are available to me. So that way I can order what is best suited for your purpose. Now, I can't really judge which one of these is which, and just to make it kind of even more take-home message, let's say that the order here flips. So my 57-degree one will come off first, and my 52-degree one will come off second. Maybe that's the way this one works. And that's because maybe A is more polar. And because it's more polar, it gets held up more inside of the column. Because you've got to remember, like dissolves like. If I have a polar positive, negative, positive, negative, positive, negative, stationary phase, and I put in a sample that is also polar, these two things are going to hang out a little bit longer with each other. And if I've got another compound that comes through that has no charge at all, nonpolar, this is just going to kind of blaze right through. So these are beginning to separate based on the structure of the molecules themselves, not really boiling points. The ones up here at the top, the 100% and 5% dimethyl and phenyl, those do separate mainly on boiling point. But the more polar I get, the more chances of me finding out it's not boiling point related at all anymore. So that's the purpose, and that's why we have so many of them. Okay. Polyethylene glycols, these traditionally go by another name. In case you ever want to know, we call them PEG, but these things can also be called carbo wax, not chrome absorb, but carbo wax. That's another industry name that we can use to describe those stationary phases. Okay? All right, so in the next video, we'll continue on with our discussion of columns and a little bit more detail about each one of these different types. But now you get a bigger, broader concept of what really is happening inside of this machine.